Hello. Hi. Good morning, everyone. Thank you for coming to the early sessions today. And also thanks a lot for the TrustX invite. Today, I'm going to share some of our learning and study about the fine-tuned large language model for smart contract vulnerability detections. So before getting started about Certic, we are a blockchain security company that were founded in 2018 by two professors from Yale and Columbia University. So we are offering smart contract audit, L1, L2, and DApps penetration testing as well. Given in the past 5 years in the industry, we're helping more than 4,000 projects perform and secure their code, and also has been secure more than $360 billion in assets as well. So before we getting started about the discussions, just want to share some of the background and motivation why we are doing such research, right? So I believe that most of the people here has been at least heard about and using the large language models such as Google, BART, ChatGPT, Meta Yamas, Copilot, many other etc. So in the past years, large language model definitely has been proving us with a really good impressions and capability in generate human-like text. He has been also start helping us in the day-to-day operations. So in our focus, the industry trend has been successfully showing the large language model, not just for the general tasks, but also with a specific fine-tuned for the downstream tasks. So what means the LLM fine-tuning? This is a process of the task that we're taking the pre-trained LLM model and then make it adaptive specifically to a more narrow detail task by training the model with a very smaller data set. So if you look at the diagram, right, we can have a customized data that will come across from any of the non-structured data such as text, image, and speech. And then we pass it to a foundation of a model. It could be like ChatGPT or Copilot or many others large language model here. And then each of the tasks, they can pre-trained it to be performed well. For instance, some of the tasks were answering like Q&A question or answering particular type of related challenge. Some of them they can answer better on the sentiment analysis. And in Certic, we are interested to fine-tune a model that we're particularly answering for the smart contract vulnerability detections. So in the past, in our space of a smart contract security, there are a few of the researchers that are exploring what LLM can be done in the field, right? In the past couple of months, we have receiving a lot of research paper has been rolling out. And after reading all this great paper, we can categorize researchers actually exploring in two directions. One is let the GPT or LLM model to do the smart contract audit automatically. And the other one is let the GPT help with the manual audit. So in Certic, we are more interested is to build and fine-tune a model that can help with our security engineer doing their code discovery. So here is our goal. To obtain a fine-tuned large language model with a Certic auditing data that can assist the auditor to discover our code vulnerability. Now, a little bit more detail is how we define assist, right? Assistant. In here, we're categorizing into three things that we want to do. First is finding the vulnerability functions and write a description, meaning that we can expect the LLM model to telling us where the function is vulnerable and also like providing a lot more description into it. The other one is tell us the vulnerability category. For instance, like we can expect the LLM model to telling us if the function is vulnerable with math issue, gas issue, or maybe like logical issue, etc. And the last one is very simple. It's a binary classification. Let the LLM telling us, okay, if the function itself is vulnerable or not, it's a yes or no task. So if we dive deeper, right, as we mentioned, we're going to have a data, pre-train the data, send it to the base model, fine-tune the model itself, and then empower with more specific knowledge base, which is our Certic data. And then over the supervising fine-tune process, we will obtain a fine-tuned LLM model. In here, we have to decide what are the base model we are going to choose. So we tried with several base model, but we were all initiated with the Meta Llama family, just because it's an open source, it's free for research and commercial use. And Llama 2 also a model that were pre-trained with more than 2 trillion token size, and also it contained with a context length more than up to like 4K. They also provided with a different model size, such as 7 billion parameters, and also 13 billions, and even bigger one with a 7 billions. In our experimental today, the result that we're going to share is the 7B and the 13B. An other base model that we try is called CoLlama. So CoLlama actually is a fine-tuned model based on Llama 2, but they were specifically trained with the correlated data, meaning that CoLlama will be performed better in terms of a correlated analysis job. So here the key result is, the key point here is that Llama 2 is more serving for the general purpose, and CoLlama is more, like working with a correlated specific data. And both of them we're going to try with a 7B and 13B parameter size. So now we choose the base model, we have our data. What are the next steps? The next step is we have to fine-tune our base model. But we all know that the large language model have more than billions parameter size, right? If we are training all of them, it would be very costly. So we use the PEFT parameter efficiency fine-tuning method. This is the only adoption that we can use a very smaller number of model parameters, and we can get a better performance compared to the full fine-tuning process. And now we have the base model, and how we're going to fit our static data into this model is we have to do the labeling on each of the data that we are passing. So we have to classify the function. We have to tell the model itself if the function has been vulnerable or not. And this process is called like supervising learning. So in here, from the diagram, you can see that we have a data, and each of the data were mapped with and labeled with the finding categories and also some of the finding. By giving these data, the model itself can be learning different patterns of the vulnerability, and also being able to predict what kind of vulnerability category it will fall into. And in terms of the data preparations, since this model is only focusing on the solidity, so we're extracting 41K of the solidity functions. 21K of a function itself is come with the security issue, and it has been distributed into this 8 different vulnerability categories. For instance, the privileged access, the math operation, logical issue, gas optimization, etc. And the remaining 20K, it will be randomly select the function that have no security issue with. So meaning that we have one additional category that will serve as a negative phase, which is non-vulnerable. And like many others, like training model, we split 80% used for the fine-tune and 20% used for testing purposes. So now this is the data structure that will look like for passing to the fine-tuned structure. We come with 3 different sessions. The instructions where is the customized prompt. We're telling the model what you need to do, what kind of area you need to solving the challenge with, and also what is the giving input. In here, since this is a structured example from the cases that we want to train the model to tell us what is the vulnerability categories. So for the testing data, right? The test data, we're only passing 2 parameters. The first one is a customized prompt, and the other one is the functions. And the function that we use for testing is something that is a new function that the model never seen. It was not in the fine-tuned data sets, right? So this is what we expect the model to tell us. Is that like correct or not? Or what kind of a vulnerability is falling into? Just a little bit narrow detail is the customer prompt. In each of the, we are not just telling like what you need to do, but also giving a little bit more context about each of the vulnerability definition, so that the model itself will have a better understanding what they need to do in order to return the result. In here, we're also sharing some of the setup, like quick setup, like at the end. By these presentations, we are actually at the end, we're choosing the base model we've come across from the Llama 2 and CoLlama 13B parameter size. the hardware, and also like some of the time estimation for each approach of the training. Now, before we're sharing the result, we have to tell maybe like doing a little bit sharing on the evaluation data sets, right? So we randomly select like 1,000 functions in each of the testing data. And you can see like around 40 of them, they are none of the vulnerability. So meaning that there is no functions, and remaining 60% not equally distributed, come across with the 8 different vulnerability categories. But many of them, they are come from the privilege, access, and logical issue. So you guys might have a curiosity why we are not mentioning even the 7B, right, where it goes. Okay, before we starting the fully training, we did a smaller observations. We tried with a smaller model, fine-tune the smaller model, which is the 7B. In this table, you can see the second column is the expected response, which is the ground truth. And the third column is what the 7B model response looks like. Unfortunately, it's not quite working well. Many of the response you can see is not making sense. And even one of them is like really interesting, is like the second one, when we were expecting the model telling us it's language specific, you can see the response. They are not directly answering our questions. It's echo back with a question to us. So this is a little bit crazy expectation. So that's why we paused the experimental on the small, fine-tuning the smaller model, and then switch to a larger one, which is the 13B. So this is the actual result that after we were doing the study. From the table, you can tell that Llama 13B model actually is still achieving a better job than Llama 2. And remember, in the previous slide that we mentioned, Llama is trained for a specific code-related task, and Llama 2 is more general task. And in here, but I mean, you can tell like the difference, even though they're achieving better, but it's not like too much what we're expecting, right? And one of the facts that we found out is that the Llama 2, which is the general task model, will take over 90% of this function are logical issue. So you can see like from the sample evaluation data, logical issue is around like 15%. And beside that, the precisions with the 36% that will come from the Llama is, even though 36 is not too great, but actually it's also better than, it got like cite from one of the paper that David shared this year. In the paper itself, it cited like GPT has around like 4% of the precision. This is really similar, for the vulnerability detection scenario. So now you might have a question, why we are particularly highlighting, the persistence versus the recall-centric, right? So if you think about the smart LLM that were the definition that we are defining at the beginning, we want to have a fine-tuned LLM model that we're helping, security engineer to discover the vulnerability. So you can think about this as an alerting system. It provides insights to the engineers. So if we have 3 alerts generated, and one of them they are correct, then it's around 33%. If 3 of them they are correct, it's 100%, that's the perfect case. But if we have 2 of them also correct, it's a 16.6%, which is also like better than the random guess. So, so this is why we were thinking like persistent centric would be better than recall centrics. And also the model itself we try with other attempt. Remember, like on the first system means like can we finding the vulnerability functions and write the descriptions. In here, you can see like if you're taking the first look, right, it looks like the model actually responding something meaningful. But if you dive deeper to understand what it's trying to say, this is nothing related to the vulnerability that were come across from the input functions. So meaning that they are creatively generate something that were not making sense, mostly. And the other attempt that we also share is like the binary classification. We just want the LLM model to tell us, okay, if the input functions is vulnerable or not. And we can see like the model is come across as like with a persistent like around 57%, accuracy 54%. Unfortunately, we were not saying like this is a really good result because it's just a slightly better than the random guess. So some of the future works, we still think about how to improving the model is to fine-tune with a larger model, because by the early stage experimental and observation, we already tell that model size definitely play a critical role, which Llama 2 7B perform much worse than Llama 2 13 billion size, right? And the other one is like refined with the high quality data. There are so many studies already been showing that high quality data at 100 level, you're already enough to improving and obtaining a good performance model. So some of the summary about this talk is like, we are concentrating to fine-tune a large language model for smart contract detections, and our goal is to assisting for the human auditing process. And the other one is like, the model we achieving is the persistency-centric with a 36%. And for the future works, we are still working with a large language model and found ground with a better data sets in order to improving the general performance. Yep, thank you so much for, this is all the sharing.